All right, so welcome to part 4 of our networks topic, and this is our final part. Today we're going to talk about trees and in particular minimum spanning trees. Now, a tree is something that contains the smallest possible number of edges necessary to make all of the vertices connected. For a tree, the number of edges in it equals the number of vertices minus 1. And you can see in the network on the right-hand side here that the tree is all of the edges that are bolted out, and they are obviously all connected. We're asked a question here, how many edges will a tree of 10 vertices have? Obviously 10 minus 1 equals 9, so that's how many edges should be in a tree for one that has 10 vertices. The one on the right hand side has 10 vertices, so let's count if there are 9 in there. 1, 2, 3, 4, 5, 6, 7, 8, 9. Now what you'll also notice is there are numbers next to it. Now if you remember back to the last video, we spoke that numbers on the edges are called weights, so this is called a weighted tree. We'll get going a little bit further with that as we go. Now let's make an example here. Looking at this graph, there are 5 vertices. 5 minus 1 equals 4. So that means there are going to be 4 edges used to make this graph connected. Now we can use any 4 we like as long as they are connected. So I'm going to do 3 scenarios here. Let's do one down here. There are 4 being used, all right, and it's connected. All of the vertices are connected. There's one of the trees. We could have also used this one, make them all connected, or we could have used that. It does not matter which one we used because all we were doing is making a tree. Now, minimum spanning trees are different. Minimum spanning trees are very specific because you need to take into account the numbers that are on each edge. We are interested in the smallest numbers. So a minimum spanning tree is a spanning tree for a weighted graph whose edges add up to the smallest possible result. Now, actually a process that you can follow. I'm going to keep it up there. You can keep it paused if you like. I'm not necessarily going to go through it word for word, but that's just there in case you need it. Basically, what we need to do is we need to choose any of these vertices to start at. Let's start with this one in the middle. The process you need to follow is that you need to work out what the smallest possible edge connected to our vertices is. If we've chosen this one, we can either choose 7, 3, or 8. Obviously, 3 is the smallest. What we do now is we repeat the process. So from either of our vertices, because we've got 2 now, we need to choose the smallest possible edge. So we've got 14, 10, 7, and 8. Obviously, 7 is our smallest. Again, now we've got 3 vertices. We follow the same process. Is it 5, 8, 14, or 10? We've got to think though. 10, we've already connected these vertices, so we don't need to worry about 10. That's not an option for us because we've already got that edge and those vertices connected. So we're interested in either 5, 8, or 14. Obviously, the smallest one is 5. Again, we repeat the process until all of the vertices are connected. So we need to get down here. Is the smallest way 6, 8, or 14? Obviously, it is 6. Are we connected? Yes, we are. We're connected here, 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 here. We've used 4 edges. What we then need to do is work out what the actual weight of this minimum spanning tree is. So what we do is we go 3 plus 7 plus 5 plus 6. So the weight of this minimum spanning tree is 21. Got that animated there. Now that brings us into directed graphs. Directed graph or a digraph is a graph in which each edge has only one direction. Now this one should have that little direction in there. The digraph here is asking us to investigate whether vertex I is reachable from A. So can we get to I from A? Basically, we've got to start at A. So if we start here, which way can we go? Well, we can either go to B or we can go to C. Let's go to B. Once we're here, all right, I can go to E or I can go to C. let's go down to C. Now that I'm here, I can go to F or I can go to C. Sorry, I could go to D. If I go to F, you'll actually notice that once I get there, I'm not going to be able to do anything. So I'm going to stay away from that. I'm going to go down here, and down here, and that takes me to I. So yes, you can get from A to I in this directed graph. If you had gone some of the different ways, though, you'll notice that it might not have worked for you. So if you had gone from A to B, B to E, once you're here, you could only go to there. And once you're there, you can't go anywhere. Okay, so it might be a little bit of trial and error with some of these different things. Now, we can actually represent this on an adjacency matrix representation, where each edge only appears once in the matrix, though, unlike matrices representing undirected graphs. What that means is, if you remember back to matrix representations, when there's a loop, we count that as 2. Well, in this, it would only count as 1 because that loop would have a direction. Think of it like a one-way street, where you can only go the one way around, so we only count it as one edge. Now we're actually going to display this information in an adjacency matrix right here. And again, it should be fairly straightforward following the process that we've been following for our adjacency matrices in the past. You've just got to think and go through it from here. Let's start at A. From A, you can either go to B or you can go to C. And we can only do that once. B or C. From B, you can either go to E or you can go to C. So we put a 1 in each of them. E and C. So there's going to give us a bit of an issue, but we'll keep being patient here. When we get to C, we can either go to F or we can go to D. F and D. When you're at D, you can either go to A or G. A, G. When you're at E, you can go to F, and that's it. You can go to F. When you are at F, you'll actually notice that you can't go anywhere, can you? So it's because all of the paths are leading into F, but none are going out of there. So all of them will be 0. When you're at G, you can go to I, and that's it. G can go to I. And finally, when you're at I, you can go to F, or you can go to E. F and E. Now, between all of these would be zeros, right? So there would be zeros everywhere in here. Right, so this would be what our adjacency matrix representation would be for this directed graph. The last one is dominance. Digraphs and their matrices also can be used to show dominance. What dominance is basically exactly the same as a directed graph. Right, but what we can do is we can say that we can call them teams. So team A, B, C, and D. In this diagram, A dominates B and C. B and C. B dominates who? Well, B dominates D, and that's it. So that would be the answer. Who does C dominate? Well, that dominates B. Who does D dominate? That dominates A and C. A and C. And then we would draw an adjacency matrix to represent this. Why this is important is you might be given real life scenarios, like if we were to call all these 4 basketball teams, well, it says that A had 2 wins out of 3 games. B had 1 win out of 3 games. And you can actually start to make ladders and make real life adjustments to these sorts of things. What I'd like you to do is have a go at the adjacency matrix for this graph right here in front of you now. Right, and if we have a go at creating this adjacency matrix, we know that A dominates B and C, B dominates D, C dominates B, and D dominates A and C. Everywhere in between would be zeros, and suddenly we have created our adjacency matrix representation for this dominance graph, digraph.